Sampling statistics lab, confidence intervals. I think you said confidence intervals, right? All right,
Yeah.
let's do confidence intervals. Okay. Okay. If we wanted to know the average age of registered voters in some elections, we could take a survey of the voters and use the average age as a point estimate of the average age of the population as a whole. In a previous lab, we saw that the sample mean is usually not exactly as a population mean. This difference can be caused by many factors, including poor survey design and the randomness inherent to drawing a sample, right? So that's what we were talking about before, is that, you know, you can sometimes, you know, get a mean that's not the true population mean, but it's not too far out there. And, you know, those means are only distributed. Let's run a simulation and investigate the point estimates by generating a population of random age data and then drawing a sample. Okay. Right. The Poisson distribution is a discrete probability of number of events occurring in a given time period, given that the average number of events occur over that time period. Okay, we're going to use a Poisson distribution to construct a bimodal distribution. Okay, that one is tricky. Let's see. Hang on, I'm going to switch over to mine. Okay. All right. Poisson, okay. Calculate the mean for the population and visual. Wait. Okay. Hang on. Okay. So they're using a Poisson distribution here. And I feel like I remember like figuring out why, but maybe we should have done the Poisson distribution. But really, okay, so the Poisson distribution is basically, it's similar because the idea is that the Poisson distribution says that if we know that like in a given period of time, the average number of times an event will occur X times, you know, that means that sometimes that event will occur more than X and sometimes it'll occur less than X. But then it's the same as similar to a sampling distribution of the sample means, because, you know, the idea is that if the average number of times an event occurs in a time period X, then the odds that it'll be less go up, go down as you go further away from X. So like, you know, if the average number of customers that walks into a restaurant is 5, you know, some hours you'll only see 3, some hours you'll only see 2. But the odds that you'll have an hour where you're going to see 30 people is really low, because that's really far up from the mean, which is 5. And the odds that you'll see 1 is also very low, because it's less than what the population is. So it's kind of similar to that idea. So I think it just uses Poisson to create the distribution, right? It's going to do strats.poisson.rbs. The location, that's the mean. No, or is that the standard deviation? I think that's the oh my God, what is it? No, that's the mean. Oh, wait. Hang on.
Just hit Shift Enter.
All right. Hang on. It's not really putting anything out. Hang on.
How do you get the
Help thing, right?
dot string?
How do you get the, hang on. Okay. Okay. All right. Location parameter. Size. RVS Poisson. I don't know what the hell. Okay, hang on one second.
Doesn't say.
Okay, use the lock parameter. Okay. So I'm pretty sure that the lock is the standard deviation. No, no, it isn't. Okay, it's one of those, right? So all that that's doing is it's just generating a sample distribution, okay? I don't know why they're using Poisson. I think they could have done it just using norm, but anyways, that's what they're doing. So it's saying that yeah, it's pulling in two distributions, one where the average is 35 and one where it's 10. And the standard deviations are 18. I don't know. And those are, it has two populations, right? And then it's concatenating them for some reason. Okay. Convert the population into a pandas data frame. Okay, it turned the ages, right? That's population ages. So ultimately what this is doing is that this is an array of random ages. And those ages are clustered around two nodes for some reason. And I think the idea that they're doing that is to sort of demonstrate the central limit theorem, because they want to create a distribution that's not normally distributed, and they're doing that by kind of overlaying two distributions together so that the overall shape is like two hills, so that's not normal.
Right.
So they do that. Okay, it's converted to a data frame. We're going to describe population ages, right? The mean is 42, the standard deviation is 13, the minimum is 18. Oh, it's because they're, I think it has something to do with the fact that 18 is the minimum voting age. Yeah, okay. So yeah, so that's what they're doing. And then they just draw a histogram for the whole thing. So this is our population distribution, and it's not a normal distribution because it has these two, even though this is just one, but it has two peaks. That's what makes it bimodal. So now we're going to take a random sample of 500 from this distribution and calculate the sample mean and the standard deviation. Also work out the difference between the population and the sample mean, okay? So take a sample size. The sample size is 500, and the sample is equal to population ages dot sample. Remember that sample is a data frame method that we can run on a data frame to pull a sample. The size of the sample is sample size, which is 500. Random state is just setting that. Sample mean is now equal to sample dot mean, because remember that population dot sample will pull, I believe it'll pull a second data frame. So say that again.
Random state 15. What does that mean?
Random state is just that's just a way to set how pandas determines it governs which randomizing algorithm it uses. The only reason that you put that is so that if somebody else wanted to run the experiment, they would get the same results, because even though like they're using a random method, the random method, the way that it randomizes is determined by the state.
The seed, right?
Yeah, it's the same concept. I'm pretty sure that it's the same concept. That's what that's doing. Yeah, it's the same thing. So it's just going to sample, because when you use the sample method on a data frame, what you're doing is that you're randomly pulling in n number of items from that data frame, and that's a random process. And then by setting the random state, you're sort of letting it know, well, when you do that random process, use this state so that later on we can recreate that random selection process down the line.
Right.
So sample mean is just going to be the sample data frame dot mean, because that's a data frame. Same thing as standard deviation is going to be sample dot std, because that's the data frame. Run the std method will get us the standard deviation. And now we're just going to print those out. That gives us our mean and our standard deviation. And that is the mean and standard deviation of the sample of 500 that we pulled, right? And it also wants to find out what is the difference between the mean. So what is the difference between the average of our sample and the average of the population. And that difference is fairly small. It's minus 0.03. We can see that there's a small difference between the sample mean and the population mean. An increase in sample size can help reduce this difference, right? The bigger your sample, the more likely the mean of that sample will be closer to the population mean. And that makes sense because then if you have a large population, let's say you randomly select elements that are like way out there on the curve, but when you select more elements, you're more likely to select elements that kind of balance each other out, and your mean will be closer to the population. Okay, this rule holds even if the central limits theorem states that the distribution of many sample means known as a sampling will be normally distributed, okay, even if the underlying distribution is not normally distributed. As a result, we can treat the sample means as if it were drawn from a normal distribution. And this is what we're doing. We're gonna treat the sample mean as if we got it from normal distribution. To illustrate, let's create a sampling distribution by taking 100 samples from our population and then making 100 point estimates of the mean. Calculate the mean and standard deviation of the sample means. Again, what we're doing here is simple enough. We're going to pull 100 samples from the population. We're going to take the mean of each sample, and that's each one of those means is going to be a point estimate of the mean. So basically, just 100 averages from 100 samples, and then we're going to plot those out and see that those sample means assume a normal distribution. NP random seed, the point estimates. We're going to initiate a blank list. We're going to take 100 samples and then, okay. So sample size is equal to 500 for X in range 1 to 100, because we need to pull 100 samples. Sample is equal to population ages dot sample. Again, we're pulling in a sample from the data. The sample size is determined by what we passed in. Sample size is up here. So we're gonna take 100 samples, and each sample will have 500 picks. So there's 500 elements in each sample.
Right.
Point estimates dot append sample dot mean. That's just going to add their mean right there. Convert the point estimates into append as data frame. So the point estimate is going to be data frame. Right. Yeah. So that's what they do. Is that, we have, this is a list up here. Okay. Every time we pull a sample, we're going to append the means. That'll give us a long list. We pass that list into the data frame method. It's going to get us a data frame. Then we can do point estimate dot describe, and that will just, give us statistics on. They're slightly different because I'm using a different random state than what they use, but it's close enough for government work. Yeah. So there we go. Okay. Standard deviation is 0.605. It's 0.586. Yeah. And you're going to see, what you're seeing though is that the means, because we have a large sample size, the means are not varying very much. Like there's very small amounts of variation, right? Like 50% of them are 43. The minimum is 41, the maximum is 44. And 42 and 43 cover, 50% of them. So it's because the sample size is large, the mean is varying very little around that, the population mean. All right. Let's visualize the distribution of sample means to check for normality. Okay, we're going to do point estimate dot hist. Bins is equal to 100. Okay. Yep, so we're just going to plot those out, and we see that it kind of does have a normal distribution.
That doesn't look very normal.
It kind of does. I think that this has to do with either I messed up, or it might be just because it's fractional values or something. But I don't know. Let's see. Let's look at their solution. Oh, because they do a density. Okay, and I did something different. I think I did a histogram or something.
Right.
Sorry, I have to run everything, I think. I'm just going to run everything. There we go. All right, so I got the same thing. I just plotted it differently. Same shape. Yeah, pretty much. Cool.
Yeah.
All right. What is a confidence interval? Okay. Do you have to run or do you want to keep going?
How much longer is this one?
I think it's going to be a little bit, and I also didn't get it right. And this is really the meat and potatoes of it, so it's like kind of harder.
Maybe let's return to this next time because it's getting kind of late here.
Yeah.